Okay, we can start. So yeah, same as always, we have this our GitHub page, and then the link is available here in the Collab notebook. Once you click here, open in Collab, it would open the Jupyter notebook for today's lecture into Collab, and here you can go and connect. Were you able to connect, Carlos?
Yes.
Okay, so today for tutorial 2, we are looking at creating node representations. Some typo. Sorry. Yes. Yes, creating node representations with Deepwalk and node2vec. And so let's have some introduction first at why we need to do or create node representations. Okay, is somebody join? Yeah.
Yeah, I posted the
Okay,
link.
yeah, sure. Yeah, so yeah, if you have joined just now, please go to the link which Carlos posted and open the notebook for today's lecture. So if you go to the today's date and says Graph Machine Learning Part 2 Node Representations, it should say in the code notebook column, it should say open in Colab. Once you click on here, this link, it will open this Colab notebook.
Mhm.
Yeah, once it's open, please let me know. Just do a thumbs up. Okay, so yeah, we can continue. So like similar to last time, we were discussing why graph learning is needed, and uh, traditional neural networks probably don't understand graph or connected data. So that's why we need to develop graph networks, which works on social networks or molecular structures or any form of data which can be represented using graphs consisting nodes and edges. And the core functionality of graph machine learning problem, be it like node classification or link classification or graph classification, or considering the unsupervised way in which you cluster nodes on graphs, everything has to go through no embeddings, and the core functionality of graph neural networks revolves around embeddings, which are dense vector representations of the nodes. And these embeddings are significantly important for capturing the complex relationships between the nodes in the graph. So what I mean by this is that if two or more nodes are located closer in the graph space, you would like to convert them to an embedding space, and then using an encoder function, and what you would like to have is that embedding should be close enough based on the graph structure as illustrated in this image, that node U and V are closer together, joined by one link, and once they are embedded into that embedding space, there also they should be closer together. Okay, so first algorithm we would look at Deepwalk, which generates embeddings in the node, treating random walks on the node as sentences, because then every step becomes like if you're moving from one sentence or one word to another. And at its core, it uses the word-to-vec model to learn these embeddings. So before we go to Deepwalk, we first need to understand what is word-to-vec model. Okay, so word-to-vec operates on words in the premise that vectors, these words can be converted into vectors, which captures the semantic relationships between the words. So for example, in this image, let's say you can have like dogs there. Dogs has a vector toward dogs and cats. So all the animals are together. Then you have all the cities together. And then you have all the verbs together glowing, such as like slow or fast or long, which means that if words or these vectors are appearing together in an embedded space, then they have have some, they are like similar in the meaning or in the context. Okay, so how this works is that first, word2vec initializes random vectors based on some vocabulary, and then the vectors have pre-specified dimension like 100 or 300 here. So this is the start point. Then the next core idea is that you define the context of each word. For example, if you have sentence that the cat sat on the mat with a window size of 2, for the context of sat, the word number 3 here, if you define the window size 2, which means that the meaning of sat would be changed by the first two words appearing before and after, which is the cat, these two words appearing before sat, and these two words on and these two words are appearing after sat. So this defines the local context of this word sat, and based on the embeddings of these four, you can have the embeddings of sat change. So that's how you generate training examples, that for each word in your corpus, uh, using the same example given above, one training example could be sat and the, which appears at the end, and and one example could be sat and cat, because cat appears in before the word sat, and and it will cover all the words in the context window. Okay, next is the skip-gram model, which takes each target word and then tries to predict its context word. What it means is that, like, if you given the word sat, then it tries to predict the word before and after sat. And this way you can learn contextualized embeddings of different words. Uh, because initially you started with random vectors, but given the context of these words, you can shift or move or change these vectors to better fit to the context given in the text. Once you iterate over the corpus, this iterative process allows the vector to gradually align in a way. For example, initially you will have all these words pointing into different random directions, but given some text, these vectors will realign themselves to have some contextual semantic meaning inside them. And once this training process is done, you can finalize those word embeddings and use it for some purpose, let's say sentence classification or word classification. Okay, so to illustrate that, we have a small example here. So let's start by running the, okay, let me delete these first. Okay, let's start with the importing the NumPy library here, and we'll define the context size 2 as shown in this text. So let's define context size 2. We have this raw text based on some universe, or it talks about universe, what are galaxies, what are and light years. Okay, so let's run this, and we can have like how many words are. So the total length of this, like if this is like one single string, then it's about 1079 characters. Okay, to just to find the total words, what we can do is split them. So what the split function is doing, it will split this big string based on the space between the words here. And then we can have length of the text. So we'll have 185 words inside this text. Okay. Now to
Okay.
set up the skip
I have a
gram.
question.
Yes.
So go back again to the context size. Is that like depth?
Yeah. So context size means that how many words you want to look if you're considering, let's say you're looking at this vast here,
Mm-hmm.
then how many words you want to look before and after vast.
Okay. So that's
Yeah.
the boundary. That
Yeah,
like,
boundary. If you define like boundary around this word vast, then what's the they can define it like a radius around this centered at vast, like how many words it will capture.
okay.
Yeah. So once we have the skip grams, like for example, that's what like Carlos asked, that how this context will help to develop skip grams here. And once we have the skip grams, we will have like 181 skip grams. So you can think of it like a sliding window that you start from, because there is nothing before this word, the or even the universe. So first word you will have is, because you're saying context size equals to 2. So that's why your counter will start from the word is, and the skip gram for the is will contain the word the universe. Okay. It will contain the universe and a vast here, because we have defined context size equals to 2. So that's why we have here. So that for first word this, and now we are just printing out the first 20. So for is, the third word, we have the skip gram model as the universe a vast, because there was the word is between, like on the third position here, and so on and so forth. You can define for all the words, and it will go till the last second word, I think from in here, like in, so that the context or the window ends at these two words. That's the total length. Because also you can see from the length is that since we are starting uh, skipping two words from the beginning and skipping two words from the end, we are actually getting 184 skip grams. Okay, now coming to vocab. So vocab is just a collection of all the words appearing in the text, because like you can see this word is, which has the same, like some context for this word the universe and a and vast, but we have the same word here is, which has a different context based on history, it, the, some. So now we'll define vocab, which is just take the set of all the words, and then if we print the vocab size, we'll find, okay, there are like 121 unique words inside uh, this text. Okay, now what you're saying by setting the hyperparameter n, that for this we would like to have an embedding size of 10. So what this means is that we want our words to be mapped into a 10-dimensional space. So for example, initially we talked about 100 and 300, but right now for this very toy example, we are just mapping them into a 10-dimensional space here. And for word2vec, I'm using the gensim library, which has an inbuilt word2vec formulation. So if we can import that from here, and then we pass our text, that, okay, this is the text we want to embed. What's the vector size we want, which we have mentioned as 10, and then the window size is 2. Okay, so once we run this, what we'll see that since we had 121 unique words, it mapped all the 121 unique words to a dimension of, so each word is embedded into 10-dimensional space, and that's why our whole weighted embedding matrix has a size of 121 by 10. Okay, now what we can do is train this, uh, and once it's done, we train these for 10 epoch, which means that for each step, it will shift the vectors or move the vectors to make them more contextualized in the 10-dimensional space. And if you want to see the first word, so for example, if let's say our first word of our vocab is, let's say, which, okay, no, okay, yeah, cooling. So this is our first word, cooling. So now if we see the first embedding for this word, now we can see, okay, these are some numbers, and now this formulation has mapped that word cooling into some 10-dimensional space by giving us a embedding of, like, or a vector of length 10. Same goes with our last word, since we have 121 unique words, so we can just print the last one, and we also see, okay, this is
Well,
mapped into a 10-dimensional space.
another question. So
Yes.
how did you choose 10? Or what is
Just randomly, I could have
no,
chosen
but
any other number.
what if you say 2 instead of 10? Then everything is going to be mapped into a 2 dimension.
Into, yeah, but the issue with low size is that it may not be enough to map everything correctly.
So 10 is just
Just some number.
because you have 121.
So I don't think there is any relation with this 10 with 121.
Hmm.
I could have, let's say I could have chosen like 100. and run the same again. And it would have mapped it to like 100.
Yeah.
Yeah, with the size. Yeah, I should just mention 10 here. Yeah. See, now it mapped it to 100.
Okay.
Yeah, I can just still run the same. And now we have same
Mm,
word represented into like a space of 100 dimensions.
okay.
Yeah. So I'm not sure like what's a good number, but you can like fix some things and see, okay, this should be enough because if this increases, then, and if there are so many words, then you need to have like larger memory size to store a
Mhm.
bigger matrix.
Okay. Computation time, probably.
Yeah, more computation time. So but I think this is just like a very small example. That's why I chose it to be 10, but 100 is also okay.
At some point, you are going to be computing distances, Euclidean distances. So
Yes, yeah,
that's
Euclidean or
some
cosine,
squares.
this could
Yeah.
be like, yeah, because when like if you're in a bigger space, then if you want to calculate like Euclidean distance, it will take a lot of time, right?
Okay. Okay.
Yeah.
So 10 was a good choice.
Yeah. Okay, now since we have like some idea of how what's word to vec that we want to embed all these text words because like models don't understand string of text. We need to somehow convert them into like numbers. So
Mm.
that's how there's like one way to convert them into numbers. So and that's how deep walk works is that once we run random walks over this graph, so in the order in which node appears would be same as some kind of sentences in which some words are appearing. So for deep work, our goal is that nodes that are close in the graph have similar embeddings. So let's start with this Erdos-Renyi graph here, and we will define random walk. And the idea behind random walk is that if you start walking randomly from each node and covering other nodes, and if there are like connections between some nodes, then it will give you some idea of the graph connectivity. And that's how each node will get like some embedding. Because let's say, okay, let's see an example and then we should be able to see. So let's define this random walk that given a graph, given the start point, and given how much of the length of the random walk you want, you can start traversing over this or randomly over this graph. So for example, this function here, I'm starting with node 0. Here's the node 0 here. And I'm saying, okay, I want to do a random walk of length 10. And then I run it. So what it's doing is that it's starting from node 0 and then and it's going to node 9. So 0, 9. Okay, then back to 0 again, then 10, okay, and then 16. So now this random walk is exploring this part of the graph, like which is the bottom part, like starts with 0, goes to 9, goes back to 0 again, goes to 10, goes to 16, goes to 18, then back to 9, back to 15, back to goes to 17, then go back to 8, and then 17. So now in this random walk, uh, we have some idea that these nodes are connected here. So visually we can see, but in larger graphs, this could be a problem. But by doing a random walk, we have some idea, or the algorithm has some idea that, okay, these nodes are appearing in some order. And this is similar to, let's say, each node, let's say, is a word, then if nodes or if words are appearing in some order, we were able to map those words into some vector embeddings. So that's the same idea behind Deepwalk, that if nodes are appearing in some order and each node is a word and each random walk is some sentence, then we should be able to assign each node with some vector or like some n dimensional vector, which will have its location corresponding to other nodes in the graph in that n dimensional space. So this was an example of random walk, and if we do it like for each node multiple times, uh, we'll have like some idea of how each node is connected to each other. So next what I'll do is I'll traverse over all the nodes for this graph, and then for each node, I'll do 80 random walks with length 10. And here also this number 80 is just arbitrary. Yeah, there's no, I don't think there's any logic behind it. Okay, I just picked a number here just to say how many random walks for each node I want to do.
But isn't that 80 random between 1 and 80? Because in range,
No, yeah, that's true.
so all the nodes will be between 0 and 80 at some point.
No, node starts here.
Okay.
Yeah. Yeah, it is just that, okay, how many random walks you want to do between 0 and 80. Is it
Okay.
range 80?
No, but those
No,
are
yeah, range 80 will not give you a random number,
you
right?
have
Range 80 will give you numbers
19,
from
you have
0 to 79.
okay.
Yeah, this says that, okay, how many times the random walk has to be repeated. So for example, if you run this and see the first 20 examples, each one of them is length 10. And let's see the first two, because see, it starts 0, 9, 0, 14, 19. See, 0, 9, 0, it
Mm.
goes to 14, 19. So now this random walk is exploring this part of the graph.
So
Next, we see 14, 19, 8, 6. So now it is exploring 14, 19, and then
so
8,
those
6,
are
this
80,
part.
80 trajectories, right?
Yeah, you can say like 80 different random walks for each node. Yeah, 80 trajectories is also good. I think you can say that.
Okay.
Yeah.
Thanks.
Yeah. So now, since these are, you can consider them as like all sentences, because now each node is a word and they appear in some order. We can have the same word-to-vec model running on this. And now what we see that is that it produces an embedding matrix, because we had 20 nodes here. This starts from 0, ends at 19. So there are total 20 nodes. And since we set the vector size is 1000 here, so we'll have this embedding matrix of this shape 20 and then 1000, so that each node is embedded into 1000 dimensional space. Once we train this, yeah, now the model is trained, and I plot the same Ardor-Sereni graph here, and just to see that. And then what we can do, and why did I plot this? Because let's say if we want to know what's the most closest node or most similar node to node 15, we can run this. And now it says that based on the similarities, and probably I think they are doing some distance measure at the back end to run this most similar. And so right now it tells me that, okay, node 17 is the most similar node. And we can even see in the graph that 15 and 17 are the close to each other. Then next is 9. So now 9 is also directly connected to 15. Okay, next is 10. So why 10? Because I think because 10 is connected to 17, and that's why we have node 8. And because it's also connected directly to 17, so this gives you like some idea that, okay, these nodes are appearing together in the graph, and then we would like to map them into some 1000 dimensional space where they also appear together. Okay, let's take an example of the Zachary's Karate Club graph from previous tutorial. So once we have this, and here also we'll do the same analysis, and we'd like to see that, okay, how Deepwalk defines the neighborhood of each node, and is able to find out embeddings for each node in like say a 1000 dimensional space. And for that, let's label these nodes. So in the Zachary's Karate Club graph, there are two classes, 0 and 1, and then based on that, we will label it. So now it tells us that all these nodes which are in red are in one class, and then all these nodes in blue are into another class. And based on our deep walk formulation, we would like to do a node classification task later on. So let's start with deep walk first. Similar to previous example, we define a walks list for each node, which are 34 in number, starting from 0 ending to 33. We'll do this walk 80 times. And now instead of 10, we are running, since this is a bigger graph, So now this, we are expecting the random walk to do 20 steps. Okay, let's print for walk 0. So now they can see that, okay, this starts from 0, goes to 13 here, goes to 1, this 1, and then 21. So now, right now it's traversing into the nodes which are blue, belongs to class blue, then come back to 0 again. Okay, then goes to 7, then 3. So now it's just traversing into the blue part. Okay, but there would be some examples where it crosses this blue region, goes to the red region and traverses. So in that way, it will learn some connectivity information. Okay, let's train the node2vec model. So now we have these sizes. There were 34 nodes. Each node has embedded into 34,000 dimensional space. Once we build the vocabulary, it might take some time. Okay, because I have set the number of epochs is 100. Okay, now it ran, and now we can, since the model is trained now, we can ask this question, okay, based on the Deepwalk model, which nodes are most similar to node 0? Once we run this, we'll see it says node 4, 10, and 5, 6. These are the most similar nodes to node 0. We go back to our graph and see, we can see that these are all directly connected to node 0 here. 4, 10, 6, and 5, and these are all connected to each other as well. So that's why these are most similar to node 0. And we can also see that for nodes which are connected to each other as well as to node 0, their score or similarity score to node 0 would be similar. So for example, they are all into like 0.73 range for node 5 and 6. Okay, since our embedding size we put 1000, so we cannot visualize it, but so for the visualizing that, we can reduce the dimension using TSNE, which is a dimensionality reducing technique, and plot it into 2D. So you can import TSNE from a scalar library, and uh, based on these embeddings, we can run these onto the embeddings and can have these node text, and then we can plot it. Yeah. So here what we see is that on the right, this is the actual graph we had, and on the left, these are the 2D representations of the 1000 dimensional vectors which we obtained from Deepwalk. And we can see that it has clustered everything in the blue together. In the red together, there's only like one outlier, which is like number 8, which is appearing here. But since TSN is like non-deterministic, you can probably run it again. You may have something different. Let's say I change the random state, then you might see like some different results. Yeah, again, it says that, okay, node 8, although it is labeled as blue, but based on this formulation, the model thinks that node 8 should belong, or it's closer to the red nodes here. Yeah, and now since that we have the embeddings and the labels, we can train a classifier on it. And the best thing about graph-based, connectivity-based learning is that even with like very few examples, you can tell a lot. So for example, uh, we can have we can have the random forest classifier and this accuracy score from the sklearn library. And based on this, we can say, okay, imagine that node 246, so on and so forth, till node 24 belongs to the training part. Based on the embeddings of these nodes, we would like to predict what classes the other nodes have. So we already like know the actual classes, but let's say if we just had these nodes and we would like to predict the classes of the node, let's say how this model performs. So we can set up train mask and test mask here. And what this formulation will do is that for all the nodes 0 to 34, it will just pick the embeddings for nodes 246 till 24, put them as input data. Same goes with labels for all the nodes, this 2, 4, 6, 8, 10 till 24. And then we can train this random forest classifier here. And based on that, we can predict the labels uh, based on this model. And since we already have the ground truth labels, we can have the prediction and then compare how the prediction based on the Deepwalk model compares to the actual ground truth label. And we see that once we run this, see that it has a good accuracy, like 90% accuracy, showing the power of this kind of formulation.
Question again.
Yes.
So you may select a different train mask,
Yeah.
and then you will get different accuracy, right?
Yeah, I think so, because yeah, I think it just depends on our training data. Like
Yeah.
we can do it. Let's try. We can
But just change just
one. Okay.
one or two, and then put it in the other
Okay.
side.
Okay. So I'll
Delete.
delete 22 and 24. I'll put it here.
Okay. Delete the comma,
And yeah. Yeah.
and then 22 and 24.
Yeah.
Okay. And you get a different.
Yeah. Probably, because see, now our training mask is limited. So
Yes.
maybe node 22 and 24 were important. Let's see. Where is 22? Here. And 24 here. So maybe if you don't have this, then connectivity information about like 25, 27, 31 is lost, or not completely lost, but it's reduced. So it might affect it. So let's say,
Mhm.
yeah, let's run it again. Okay. And so now see, you are
Yeah,
like
very
now
low.
up to
Okay.
75. Yeah. If
Mhm.
you add some more, then probably you will see a higher accuracy, I think.
Yeah, just put another set of two, like 5 and 7, or 15 and 17,
Okay. So I'll just put here
and
and
delete
then
them,
remove 15 and 17. So most probably it should improve,
and delete the
because now
last
you
two.
have, now your training data is more. It may or may, I'm not like, these are like small examples. I'm not very sure, but see, it's
Yeah.
90%. So,
Okay.
so
So
maybe this tells you that adding 15 and 17 didn't really do much. Mm.
that means that it's dependent of what you use for training.
Yes.
And so I guess the selection is just visual. What
Yeah, I
has
think so.
more
Yeah, right.
connections or
Because
not?
like, for example, 15 and 17 maybe are may not be really helpful. Like 15 is in the red part here, 17 is somewhere else. I don't see. Yeah, here. So
Mhm.
maybe node number 17 doesn't tell you much about the graph connectivity, because maybe let's say if you like remove 0 and 33, then
Mhm.
it may affect.
Okay.
Like for example, let's say we add 0 and 33 in the training. Let's say how it, because those nodes are very important, right? So now, yeah, okay. Yeah, now we are back. What we did is just added 0 and 33 into the training mask. And let's see now. Yeah, so it didn't really change much.
Mhm. So you have to play.
Yeah, play around. I just chose like some odd numbers, some even, to set up this example.
Okay.
Yeah, but what we can do is that just let's go back to the original formulation. Yeah, here. So, but let's say we fix the train and test for all the examples, then we should be able to see that how different models perform. So right now we are at 90.91, but
Mhm.
let's say now we can go to like node2vec and see how does it perform. Okay. Yeah, so coming to node2vec, essentially it's based on deep walk that we are doing random walks, and then later on using word2vec. But here in node2vec, there is an introduction of bias into random walks that based on some parameters. Either you would like to go depth-wise or breadth-wise, and and to understand that, we need to define like the neighborhood of a node with flexibility. So node2vec says that both DFS, both BFS and DFS capture valuable information, and like the definition we looked at in previous lecture, that BFS highlights structure equivalence, like in the neighborhood or in the vicinity of that node, that what nodes sharing multiple neighbors are similar. But DFS explores broader network property because it uh, goes deeper into the network. So that also can define some kind of connectivity for the whole network. And for BFS and DFS, it defines two parameters, P and Q. Okay, and which influence that if you are at a node, would you like to go back to the previous node or explore new areas? And this defined with parameter Q, and then the parameter P, and parameter Q defines that uh, if you are at a node, then what you would like to do a BFS or a DFS. And so if I have to say it again, P defines that would you like to go back to your previous node or go into a different node which was not visited before. Uh, Parameter Q defines that either you want to do a BFS or a DFS here. Okay, okay, so I have this function next node which works on your graph G. It has a list of nodes which were visited previously, and it has a list of like, okay, what current nodes we can visit, and then P and Q. And based on these parameters, it can judge whether it wants to revisit the previous node or want to go to a new node, or either even if it goes to a new node, uh, does it want to do a BFS or a DFS at a node. So, and then our random walk goes in the same way, that we define the graph where you want to do a random walk, and then define the length and the start of that node and the length of the random walk, and parameter P and Q. Yeah, so now we are back to our karate club graph, and here we would like to do random walks. So I have four examples here. Yeah, and then we have different values for P and Q. So in the first one, we have small p, P and Q both small. In the second one, we have smaller p but larger q. And in the third one, we have higher p and smaller q. And the final example, in the fourth one, we have both p and q values higher. How it's going to affect the behavior of a random walks is that if both are p and q are higher, you're discouraged from returning the previous node, and then but you will still explore the local neighborhood of that graph. Okay, this was the last example here. Okay, the other is that if you have low P and high Q, which means that you will go back to your previous node, but then since the Q is high, you will keep oscillating between three nodes, like just very few number of nodes, and focuses on just getting the local embedding correct. Okay, the third case is that you have low Q and high P, which means that now you are uh, not going to the previous node, going to a new node, but you want to do a DFS-like search and explore the distant part of that graph. And if you have both P and Q low, it means that, okay, you are although going to have a DFS-like behavior, but you will just keep going into very, very deep paths with and overlook local structures. So yeah, I've summarized all the behavior of P and Q and how it changes into this table. Yeah, you can.
How do you optimize the selection?
I don't know. It's like since these are like you can say like hyper parameters, that whatever works best, you can pick them
Okay.
based on the graphs, I think. Because here this 110 is just randomly I chosen just to say, okay, what is bigger, what is lower.
Mm-hmm.
Yeah. Okay, and then we have the same formulation. We define a list with box, we do random walks for all the nodes present in our karate club graph and do it 80 times. But the difference is that, okay, now, and then we have the define the length, but we have different parameters here, 3 and 2. So this 3 is P and then 2 is Q. So based on different kinds of like problem, we can change P and Q. Okay, let's doing some walk. And again, since now we have the random walk order, we can do this word to vec formulation here. Yeah, here. And then we can do node to vec train. Okay, so now this model is trained and now we can ask this question. Okay, which nodes are similar to node 0? Okay, so now this tells us that nodes 6, 4, 10, 5, and 13 are similar to node 0. So we can go back and see that, okay, 10, 4, 5, 6, and 13, which are like directly have connectivity to node 0, is more closer to, in the embedded space, these nodes are closer to node 0. Okay, similar to like previous example, since we have this 1,000-dimensional vector, we can plot this into a 2D plot, and using TSNE, we can see. So now, see, the difference is that all the nodes are clustered together, and there's like a huge gap between these uh, two clusters here, and then still misclassifies number 8, because like in previous example we found that, okay, there was not enough gap between uh, the dimensions of these vectors, but using the node2vec dimensions, we have a significant or like a gap, or like you can say, if you had to classify these, you will find a very nice margin between these two clusters.
Okay.
Okay, and then we can do the same formulation again here, which was same as done in Deepwalk. We have the same masks here. We run it and then we can train this and see we get like 100%.
Mm.
Yeah, which means that you doing biased random work based on those parameters can provide or can generate better embeddings. Yeah, yeah. And then I think it's stochastic, because when I run it, it gave me like 95%, but right now it's giving 100%. So
Can you do that? Run it again. See if you
yeah,
have
sure. Yeah, I
numbers.
think it just depends on TSNE.
But the seed vector, the seed random
Oh yeah,
seed.
yeah, I can just change this. Yeah, TSN has like a lot of parameters, right? Like perplexity, what distance you want. So right
Mhm.
now I think the default is Euclidean, but let's say if I change it to cosine, then it might change. So yeah, I can just run this. See, now the order, or like the arrangement has changed, but
Mhm.
if I do the same, I might get some new number here. Okay, still
Uh,
getting that. Okay, I can just change this. Oh, still
I,
getting 100.
I
Yeah.
never trust 100% accuracy.
Yeah, I mean, yeah, because see, I put it 95, because when I developed this, I was getting like 95. So
Okay.
yeah, let's say like change perplexity, put it to 10. Perplexity just means that to calculate the distances, how many neighbors it's going to look at. So now we may have like some see different plot, completely different plot here. And now this might affect your uh you see it's again 100%. So yeah, I don't know what's happening, but yeah.
Okay, so that's fine.
Yeah. Okay, the application is that you can make a recommender system, because now so the idea behind this is that some node, so the labels of some of the nodes, but given some new nodes, can you predict based on the connectivity of the graph? So you can just quickly look at this example here. Yeah, so, okay. Yeah, so there is this data which has like different movies and the rating and which user gave the rating. And then there is like movie titles there are like 1682 movies for each ID. And so first question is, how do you build a graph out of this information? So one approach is that to establish the connectivity between movies, we can see that what ratings are given by the user, and if two movies have been rated positively by the same user, we can construct an edge based on that appreciation. Like for example, what kind of rating is provided by the same user for different movies. Okay, and this approach allows us to construct a network where like, we can just based on the user preference, we can do a build a recommender system using this. So right now what I'm doing is to filter this whole so there are like so many ratings available. I'm just filtering all the ones which are equal to or greater than 4. So once I filter this, I'll have the number of movies or the number of reviews which are either 4 or 5. Okay, now I will make an edge between those movies here. So right now I'm just iterating through the user list and just seeing that okay, what movies are rated by the current user, and if these movies are together, then they'll say okay, these movies appear together, and those should have an edge between them. And then we connect the graph using this information. Uh, so right now, based on this information, we are getting 99 nodes, and there are 624 edges between those 99. And we can verify this also by just calculating the length of the array which contains the nodes here. Okay, now going to plotting. So this is what I was talking about, the larger graphs. Plotting is like plotting is a mess, like what you can see here. So that's why I put a very high score here, like the score between the edge should be more than 60, because let's say if I put some lesser score here, this graph would be very messy, and these labels may not be visible. Okay, so for that, I think so there is actually a Python package which is node2vec. We can install it here. Yeah, I might give you some error. It will say, okay, we need to restart network X, but yeah, we won't need that. Okay, yeah. Okay, just cancel. You don't need to restart the session. Okay, from here we can import node2vec. Use and say that, okay, run node2vec on our movie graph. The embeddings dimension should be 64. Walk length should be 20, and we need to do 200 walks for each. And these are your P and Q parameters. So let's start now. This function is doing random walks for all the, yeah, so it's doing 200 random walks for each node. Okay, and then we can just fit the model here. And so fitting just means that, okay, we are trying to get those embeddings aligned. Okay, let it run. Okay, try now. You can actually look at the vector embedding shape. So we began with 99 here, movies here, and each of the movie or each of the node has a dimension 64. So we can get these labels. Yeah, and these are the 99 movies, and we can define a function for example, okay, recommend, and then the function works on a movie title, and what it does is it just gives you the closest 5 neighbors based on that network. Okay, and then let's say if there is this movie Terminator 2, and let's say we want to predict like which movie is, like if you want to if you have seen this, which movies are similar to this, then we can run this and it says okay, so Terminator 2, like it's kind of obvious the Terminator 2 1 and 2 movies are appearing together. And these movies have some kind of like sense, you can say, like a time travel kind of thing, because in Terminator 2 or 1, or even in Back to the Future or 12 Monkeys, all these movies have some notion of going somewhere in time. Okay, so we have this, and also here's another example, like you can run for this movie Silence of the Lambs, where we run this, and then we'll find okay, So based on the model, it suggests, okay, these are some 5 movies which are similar and could be seen. Yep. Yeah, that's it for today, guys. Thank you. Any questions?
Interesting. Thank you.
Yeah, thanks for this. Yeah, for next week we will be we will go into actual graph neural networks and see how graph neural networks work, because right now we are just doing some uh, embeddings based on walk. There is no information flow happening between the nodes, but using a graph neural network, we'll see, okay, how you can how information can be in the neighborhood can be used to do this node classification.
Okay.
Yeah, yeah, I'll stop share now if you don't have any questions.